if you take people as a proxy for risk, the number of people in your dependency chain at build time is an order of magnitude, if not two, lower than the number of people in your dependency chain at runtime. And so think about the risk at runtime to the flow of the data, and then think about removing that risk in various ways. Ockam is one way to do it, but there are other ways. Encrypt your data when you're storing it, et cetera, et cetera. There's all sorts of ways to approach it. Don't send your data to certain destinations. Like that's also a way to remove that risk, right? But I guess my tip here is think about the risk at runtime to data flows.
You are listening to The Secure Developer, where we speak to industry leaders and experts about the past, present, and future of DevSecOps and AI security. We aim to help you bring developers and security together to build secure applications while moving fast and having fun. This podcast is brought to you by Snyk. Snyk's developer security platform helps developers build secure applications without slowing down. Snyk makes it easy to find and fix vulnerabilities in code, open source dependencies, containers, and infrastructure as code, all while providing actionable security insights and administration capabilities. To learn more, visit snyk.io/TSD.
Welcome to another episode of The Secure Developer. We're super excited to have you back, and I am very excited to be with you today because we're going to delve into a topic that's always been near and dear to my heart. I started in security in the networking space and doing some hacking on Banyan Vines networks, and I'm going back now about 30 years. But I'm joined today by someone who has a tremendous history in this. He's the CTO at Ockam, and I would like to welcome to the show Mrinal Wadhwa. Mrinal, how are you?
Very good. Thank you, Danny. I also spent a lot of time in networking systems at the beginning of my career. So it's very, very exciting to be here, and it's lovely to have this conversation with you.
Yeah, likewise. Now, maybe we can just kick off. Why don't you give an introduction for yourself to the audience and how your career started and how you ended up where you are today?
I started my career at EMC, the data storage company. And right at the get-go, the problem I was sort of solving in that team was around high availability of very large scale data. This was 20-ish years ago. And we were thinking about how do you make data available across geographies in a way that it's highly available, even in cases of failure, etc. So that kind of started this thinking about large scale distributed systems for me, right? Then very quickly that led me to other types of distributed systems problems. I became very interested in Erlang in sort of the early mid 2000s. And that taught me a lot about thinking about distributed systems and messaging and fault tolerance and things like that. And the types of systems that I got involved in then became naturally that. I spent a bunch of time in the Hadoop ecosystem doing things there. And then, about 10-ish years ago, maybe a little bit longer, 11 years ago, someone asked me to be CTO of a hardware company that wanted to become a IoT company. Right. So this company was called Fiber. They made sensors and controllers for city infrastructure. But these things weren't connected. And my job was to come in and design a system that would connect all of them. And so in designing that system and then deploying it all around the world, I started to realize that securing these systems is a pretty challenging problem, right? Because now in a typical deployment, we had 100,000 entities that needed to be trusted to not only send us information, but also to take actions in the physical world. And the application domain was fairly critical. It was like city infrastructure, water systems and red light systems. And then we had some customers that were like airport deployments and things like that. So I spent a lot of time thinking about how do we secure this large scale distributed system that's sending lots of messages at a very high rate. And that kind of led to my current job because I started thinking the capabilities we build in that IOC system should actually be general purpose, and we should be able to create secure, mutually authenticated connections from anywhere to anywhere in any kind of system, not just IoT, right? And that started the genesis of our open source project, which is called Ockam, and also the company, which is also called Ockam.
Well, that is awesome. And I'm glad that you have that start in the application software space, because most of the audience, I believe, is very much involved in software. And when I think of security in these systems, I go back to my computer science days. This is going back a while again, but I think of the 7-layer stack where you start down and you have IP and you have some transport, management on top of that, TCP and TLS and secure messaging on top of that. I guess my question is this: when people are building software, do they need to think about the security between the transport layer into the application? Or do you find that software developers are thinking about that, or they're just opening a socket and not worrying about it?
I run into a mix of those. There are people who are not thinking about it, but their systems are such that they should be considering it. I also run into people who have thought about it extensively and have tried various things to minimize their challenges. But, if you mentioned the 7-layer stack, right? The challenge with the 7-layer stack is the security protocol there typically is TLS, right? Yeah. And it's sitting on top of TCP. The problem you encounter is in a very large number of modern application use cases, it's impossible to create a single TCP connection from a client to an actual server of that information. What you end up doing is creating TCP connections to intermediaries that are usually exposed to the internet, right? And then stuff that's elsewhere is still not getting the security properties of TLS. And that's where things become very risky. And so Ockam specifically is a solution where instead of a secure channel sitting right on top of a transport layer connection where the guarantees are from only as long as the underlying transport layer connection, in case of Ockam, you can have a secure channel that can sit on top of a route described by 3 TCP connections or 10 TCP connections or a TCP connection, a UDP connection, and a Bluetooth connection. Like you can mix and match these routes of transport layer connections, but over this entire route, you can have a end-to-end encrypted, mutually authenticated, secure channel. And that unlocks a whole series of capabilities and changes the way you then can think about risk in your application. So to answer your question, I encounter both types, and it's always an interesting conversation, depending on where someone's starting.
Yeah, it used to be that your connection was kind of point to point. And well, I don't even know if that was true 20 years ago, but certainly today it's not. In fact, most of the applications we're working with are Kubernetes based in a cluster, and there's a gazillion microservices that are all communicating with one another. Do you find that the microservices behind those gateways, forget about, 1 hop, 2 hops, I find it's 1,000 hops often in applications to truly get. And then do you find those microservices typically are encrypted inside the organization, inside the Kubernetes cluster, or no?
No, usually not. People consider it, but then realize it's complex to do in Kubernetes environments. And they end up going, oh, we've got a boundary. We're okay, right? And so most often we encounter Kubernetes deployments with not enough security in the microservice to microservice communication piece. There's also termination of TLS, usually at some front end load balancer. And then beyond that, the traffic's kind of moving in the clear is the typical deployment I encounter. The better case is they'll terminate the internet-facing TLS at the load balancer and then try to set up a new TLS. But then you get into the problem of how do you do mutual authentication in TLS? How do you do it in a way that scales to your microservice architecture, and all sorts of complexities around that?
And do you think they're not doing it because because of the complexity of setting it up? It's a security versus complexity, simplicity thing, or it's just they're not concerned about it? Because most of the developers I talk to, or at least the development community that I speak with, they do care about security, but the complexity of setting these things up is what holds them back most of the time.
That's true. That's been my experience as well. I rarely encounter someone who goes, I don't want to reduce the chances that our system gets compromised, but then they trade it off against other things on their plate, right? And all the other things that they could be doing. And I think security, privacy, performance, these are all features of a product someone is working on. And unless you can tie back the features to some sort of value proposition to the end customer, it can be hard for people to justify the work involved, right? Especially if the work is complex, right?
Yeah. And thankfully, most of our audience, the developers, would care about security and would want that security. How do you think about it in the context of offline items? You mentioned IoT earlier. Can you establish a handshake with something that is not immediately available? Or you talked about multiple protocols. I'm interested in communication that goes over both Bluetooth, which is a radio transmission, versus, UDP and TCP, which are also very different. How do you do that? And well, I'm just curious on and how you do something that's offline, or how you do something that crosses multiple protocols.
So the first part of the question is fairly simple. It is possible to do handshakes with things that are offline. The way you do that is the thing that is intermittently online. That thing usually is the initiator of the channel. And the thing that can be highly available, some sort of service, can be the responder in that channel, right? And once you have that mechanism in place, then those initiators can come in, set up a secure channel, oftentimes cache the state of the channel so they don't have to reestablish the channel, and that way can save battery life, etc. And then once that channel is initialized, you can kind of keep benefiting from that channel over a long period of time and do rotations in the life cycle of the channel itself, which is important because you don't want to end up with, all my devices are communicating using the same API token, and I'm hoping no one gets that token, right? And surprisingly, that seems to be a very common deployment where people are relying on the security of one API token, and many, many, many clients actually possess it, which is unfortunate, but it's real.
It makes me feel like I'm going back to the days of SSH tunneling, where I'd establish one SSH tunnel and then I would push everything through that one connection inside it. But okay, well, so that's interesting. And obviously the end-to-end encryption and security of these things is super important. How do you deal with the performance of it? Because I have to believe one of the things that has held us back historically was that if you terminated something and reestablished, there's a performance implication of that. And that's always held developers or software developers back from trying to do this at scales. Are there ways to mitigate the performance implication of these installations?
Great question. And I also feel like I didn't fully answer your first question, so I'm trying to club those answers, right? So your second part of the previous question was around how do you do this over multiple protocols, right?
Yes.
And I think this leads nicely into how I think about performance in our system and these use cases, right? So traditionally, secure channel protocols have been designed on top of transport layer protocols. So TLS is on top of TCP. Bluetooth has a secure channel protocol that's on top of Bluetooth. Other systems have secure channel, like their satellite communication protocols that have their own secure channel implementation. And what you'll notice if you look back at history of papers published around security vulnerabilities, you'll notice that TLS over the last 30 years has incrementally gotten a lot better, especially with the latest versions. They're fantastic designs, consider all sorts of possibilities. But all the security protocols in the other transport layers usually got left behind, right? So they aren't as safe as TLS 1.3, right? Far from it usually. And they have this problem of that software in a Bluetooth stack gets shipped over very, very long cycles. You can't even fix problems, right? So with Ockam, we took a slightly different approach, which is we were like, secure channels should not sit directly on top of a transport layer connection. Mm-hmm. Instead, we inserted a application layer routing protocol just above the transport layer connection, which means that I can take messages from one transport connection and hand it to another transport connection, right?
I got it.
So I can take a message from TCP and hand it to Bluetooth. I can take a message from Bluetooth and hand it to Kafka, etc., right? So this routing protocol is just like it's like a relay race, right? It takes a packet and it hands it over, right? Once you have this, and then you place a secure channel protocol on top of it, now I can have a secure channel that goes end to end over a Bluetooth hop, then a TCP hop, then another TCP hop into my Kubernetes cluster, then another TCP hop to my actual microservice pod. And then the connection is then, the secure channel is then terminated at that location. So the end result is my little tiny IoT device gets an end-to-end encrypted channel all the way back to my pod in my Kubernetes cluster. And all the parties in the middle are no longer adding risk to my channel, right? So this basic mechanism unlocks, turns out, a whole series of possibilities, right? So I started with this in the IoT land, but think about it this way. Let's say I have a server in Ockham's Kubernetes cluster, and I want Snyk to access that server. What is the traditional approach? I will take my server and I will put it on the internet. And then Snyk will make an outgoing connection to that server and there'll be some communication, right? The challenge is now everything behind my internet exposed server, all the Kubernetes infrastructure, etc., I now have to design other ways to protect the data, right? But with this Ockam approach, I don't have to expose my server on the internet. You don't have to expose your client to the internet. Instead, we can both make outgoing TCP connections to a encrypted relay service on the internet. That Ockam offers as a paid SaaS offering, but it could be someone else running an Ockam relay, right? So you run this relay, both sides make an outgoing TCP connection to the relay, and we then set up an encrypted channel over this relay. So both our client and server are entirely private, yet Snyk can consume data from Ockham's services. And that means that my server and all the risk it gets exposed to by being internet exposed is no longer a challenge I have to think about. And so this is a different kind of use case that get unlocked with that same capability. And then I'll mention a third one before I get into performance, but a completely different one would be, there's this company, Red Panda, that launched a zero trust Red Panda using Ockam, right? And Red Panda offers Kafka-like brokers as a service. They have a special protocol for it. But at the end of the day, you have a Kafka producer and a Kafka consumer wanting to send each other data. That data goes through a cloud service offered by Red Panda. And the traditional approach with all the other Kafka vendors currently is that the data gets TLS encrypted at the Kafka client, gets TLS decrypted at the front end of the load balancer of the Kafka broker. And then who knows what happens, but it's in the clear before someone decides to encrypt it just before storing it into disk, right? Which means that if I am a consumer of such a service, I have to think about the risk added to my data by this third-party service I am relying on, right? But in the Red Panda case, because Ockam can move data through any transports, it can move data through a Kafka topics. So at the Kafka producer, the data gets encrypted. It goes over a TCP connection, stays encrypted, gets written to a Kafka topic, stays encrypted, gets read back out of the Kafka topic, stays encrypted, goes down another TCP connection, gets read by a consumer, and that's when it gets decrypted, right? So all of these topologies and all sorts of use cases get unlocked to create end-to-end trust, end-to-end mutual authentication, end-to-end guarantee of data integrity, and also end-to-end confidentiality, right?
You're addressing kind of two parts of the triad of confidentiality and integrity. So that brings us to availability or performance of this. I'm just curious how you solve that at scale when you're talking, well, just doing this in the complexity of organizations today and at the scale that they need to address. How does that work in this model?
Yeah, that question almost directly leads to the third peg in the triad, right? Which is authenticity.
Yes.
So the complexity in secure communication infrastructure usually comes from the problem of trust. So the problem plays out like this. Let's say I have one entity wanting to talk to another entity, which means two things have to trust each other. But if I have 500 things wanting to talk to other things in that cluster of 500 things, I now have to set up mutual trust in a 500 squared relationship, right? Everything has to trust each other. And that's where it gets really complex. Like, how do you set up this trust? And the traditional approach is let's all 500 trust one authority. And that authority will give us some sort of, in TLS case, certificate, in Ockham's case, a credential, and then we will sort of do authentication authorization based on that credential, right? That's the traditional approach around this. But all of this creates a whole series of complexity problems. So how do I do mutual trust? How do I manage private keys? How do I rotate those private keys? How do I get credentials? How do I rotate and revoke those credentials? Et cetera, et cetera, et cetera. And at scale, and I gave the example of 500, but our typical user is thinking of millions of such entities. And so how do I do this at a million entity scale where anything might need to trust anything else? That's where all of this complexity then sort of compounds in very hard to deal with ways. So in Ockam, we step by step thought about each piece of that puzzle. So for example, the first step was everything needs a cryptographic identity. This cryptographic identity, it will be rooted in a cryptographic key. But we never want forever cryptographic keys, right? Because secrets tend to get leaked. So we need to think about how will this identity key be rotated over time. So in Ockam, we have a cryptographic key that's an ED25519 signing key. But a key sort of idea was that each key can sign its successor into existence. And so let's say I trust your service based on its identity key. If that service decides to rotate its private key, my trust in that service is still rooted in the first identity key's public part, which we call an Ockam identifier. And so it allows your service to continue to rotate its private key over time. That means that I have eliminated a very important complexity challenge, which is how do I reestablish trust when you decide to do rotation, right? So that's one example. Another example is if you have this attribute-based access control layer that's rooted in credentials. The traditional approach to credentials is X509 certificates, right? And the problem is X509 over so many years has gained so much complexity. And the trust infrastructure around X509 is typically web PKI. And that also has over the years gained so much complexity. But the use case that browsers are going after when they're doing web PKI is different from the use case an enterprise is going after when it controls all the entities that are participating in a communication, right? So when you're trusting all the root authorities in web PKI, you're trusting 2,000 different entities, right? You don't need to in a typical enterprise application. So in Ockham's case, we significantly simplified how we do credentials. So there are authorities. There's no one true authority. We can have many authorities attesting to many different attributes in our system. And the data structure that the authority signs is very simple. So it's not, several kilobyte long X509 cert. It's a tiny 300 byte long little credential, and it has attributes in it. So you can define attribute-based access control policies. So I can spend hours talking about the details of this, but the point is the use cases that TLS and WebPKI are focused on, which is browsers trusting all browsers in the world, trusting all internet servers, is a different problem from all things in my enterprise application trusting each other, right? And so we were able to take the constraints of this other use case and design specifically for that rather than taking on the complexity of WebPKI.
You raise an interesting point there because it is true. SSL and X509 certificates are based on the browser-based world, not kind of service-to-service type world, which is what you're describing. Do you think that the emergence of WASM or WebAssembly will drive a different model than the traditional PKI infrastructure? Because what you're really doing at some level is trusting agents. When I use the word agents loosely there, out at the edge, you're trusting a decentralized, a federated model. Do you think it will cause people to reimagine what they're doing with our current security model for browsers?
Maybe. potentially, it's already kind of happening. Passkeys is an example of people thinking about trust inside a browser differently. The realization is we really need cryptographic secrets, not a passphrase humans have to remember, right? And so by having passkeys, we can have these keys be stored in safe ways, like in my secure enclave inside my MacBook, right? And so now you've got this ability to have cryptographic secrets, but to make that flow work, a whole set of mutually trusted channels have to be established, right? And if you dig into the infrastructure Apple and Google and others have to implement, you start to notice end-to-end encrypted channels in that path, right? And so I think that with passkeys and I can give a couple of other examples, people are already reimagining the traditional trust model of the internet. Because if my server and my WASM program are trusting each other based on a cryptographic key, then knowing each other's public keys in some way, then the utility of the TLS infrastructure the Web PKI infrastructure starts to minimize, and the trust in this key starts to become elevated. Another example, a recent one that I like a lot, is Apple published a paper called Private Compute Cloud a few months ago, right? And Private Compute Cloud is their AI in the cloud infrastructure. So when not enough compute is available in my iPhone, Apple will delegate some compute to a cloud infrastructure, but this compute will not terminate TLS along the path to the actual compute location, because they don't want my private phone calls to end up in log inside their TLS infrastructure, right? And so they're like, we'll have end-to-end encrypted channels all the way to some confidential compute environment. We'll decrypt the data just there, and we'll set up all sorts of controls around this confidential compute environment, right? So these are examples of, I think people are already, whether you take people using Ockam to do safe things, or these examples from Apple and passkeys, etc. I think people are already thinking about how do we do trust in a different way compared to, the traditional browser-based model that we were all focused on for a long time.
Well, it makes sense because we're becoming attuned to the more decentralized distributed model. And I guess it does make sense that we are looking at new models. If I can pivot for a moment. So in the old world, we used to do some of the security inspection at the perimeter. We would decrypt at the perimeter, and then we do deep packet inspection for whatever DLP or malware coming in. And part of our security defense was having that ability to decrypt. Are we worse off or better off in an end-to-end encrypted environment? Do we lose the ability to do that type of inspection? Like, very specific example, I worry about data loss prevention, someone exfiltrating data. And so one of the things that you typically want to do is monitor traffic to make sure that data is not leaving an environment. Do we lose out? Does the risk increase by having end-to-end encryption?
No, if we think about it properly, right? So the traditional model that you described is all data flows through a central place. That central place gets to look at all the data. Usually they do it by breaking TLS. Like that's the typical approach, right? You terminate TLS, lie about the TLS connection to the sender, and then you reestablish TLS and lie about the other side, right? That's how it's usually implemented, right? So you effectively use a man-in-the-middle attack to do inspection. That's what all of those solutions do, right? Secure by design, in my mind, is just an exercise in moving risk around. There is risk. The question is, how do you deal with it? Where do you locate it? And how do you then kind of manage it well because you've located it well, right? Locating all the risk at this central location, which can see everything and manipulate everything, not just see, manipulate, right? Yep. All secure channel protocols, whether it's TLS or Ockam, provide data integrity guarantees in addition to data confidentiality guarantees. And usually when I talk about encryption, people kind of stay focused on the confidentiality aspect. But the really important guarantee is I am guaranteed that the data as it was sent from the source is exactly as it is received by the destination. But if you intercept TLS with a man in the middle, you're losing that guarantee of confidentiality and also integrity, which means an attacker, that's the honeypot. That interceptor is the thing that an attacker really, really should get to. So it's this like very important choke point from a risk posture standpoint and highly vulnerable if someone gets there, versus if we could move all the risk of a certain piece of data to the origin of that data. Right? So if we take, hey, at this location, the data is originating. It is already unencrypted. That is the only place it's going to be unencrypted. And then it's going to be unencrypted where its destination is, right? If we can do that, then we remove this central location. But now we've got the challenge of how do we observe exfiltration problems, right? And let's build observability tools that can read what type of data is leaving these edge locations, but have no ability to manipulate the integrity of the data as it leaves these edge locations, right? So in Ockam, what we do is we send OpenTelemetry feeds out from all the ends of an end-to-end encrypted system. And you can take and consume those OpenTelemetry feeds in, wherever you're consuming your events. So you're getting the read to see if bad data is leaving. We can also give you abilities to stop with a policy-based control the data from leaving. But what you don't get is the ability to be in the middle of the flow of the data and manipulate it, right? So if someone compromises this observability infrastructure, they're not adding risk to the actual data. They could leak the type of data leaving, but maybe if you design it well, they can't even leak the contents of the data leaving.
Yeah, you're really ensuring, obviously, the integrity. I wonder if the reason why that centralized choke point was implemented was because historically security people have not had access to either the origin or the target. And so their easiest way for them to implement was at the beginning, which takes us back to development. Because actually, if you want to do a source to target encryption, it means that you have to threat model and design your controls into the source of the application or into the target of that application, rather than trying to do it in some way in the middle that breaks the confidentiality and integrity, as you say. It actually puts more burden on the developer. And it probably, I'm thinking out loud here, that's really in some ways what we're doing with DevOps. We're giving the developer more responsibility to implement those controls at the source.
Yeah, it's very hard though, right? It's hard to do cryptography well. It's easy to shoot yourself in the foot with it. It's hard to do key management well. It's easy to really, really mess that up. And we also can't convince everyone to change code in their applications, right? This is hard. So in Ockam, we approach this in two ways, right? But I have to start with the premise. I do think it has to be as close as possible to an application, ideally inside the application. So the starting point was we built a Rust library. So you can use our Rust library inside your application. And then you're sending messages that are data structures in the context of in the context of your application domain that you're sending over this encrypted channel from within your application, right? Which means now that this application developer needs easy ways of saying, create a secure channel for me. Easy way of saying, create an identity for me. Store this identity in the secrets of this identity in a KMS. Rotate this identity's secrets. All of these need to be available as single line function calls, ideally, right? And so that's what the Ockam Rust library enables, is instead of you having to think about how to do cryptography well. And I encounter this case all the time. So that's why I want to bring it up. Oftentimes people will go, oh, end-to-end encryption? All I need is a yes and a key and I'll be fine, right? Well, it turns out that's where we started 50 years ago. You need a lot more to do encryption well, right? And so if you think about forward secrecy, you think about, key compromise impersonation attacks, there's a lot of very long history around doing secure communication well. So you need really well-designed primitives. And so Ockam gives you those primitives in the form of single function calls. But we can't get everybody to change their applications. And it's a lot of work to go, oh, I have to plan a project that will change my application to do this, right? So the other model, that's the typical model Ockam deploys in, is we will run a sidecar next to both ends of this communication. Mm-hmm. And this sidecar would expose a virtual point-to-point TCP connection. So in my earlier example of Sleek communicating with a service available inside Occam's Kubernetes infrastructure, I would run a Ockam node as a sidecar next to my service in my pod. You would run Ockam node as a sidecar next to your client inside your Kubernetes infrastructure, I'm presuming here. And then over this, we will set up a point-to-point virtual TCP connection, which means that my server will appear on localhost inside your client application's pod, and you just call it, right? And we then can automate all the work. So we use eBPF to do kernel-based, highly performant encryption and network connections. We can automate the storage of keys into KMS. All the complexity then can be removed from the end customer. And the user, all they have to do is change the listening address to localhost and the client address to localhost, and everything just works from there, right? So that's kind of the way we've taken to simplify all of this complexity and make it easy for developers to adopt it.
And I'm a big believer that the way that you secure applications is not through refactoring and super smart people. It's actually the opposite. It's being able to add something super simple and making it easy for developers. I always say, use another security example. I always say the reason we got rid of buffer overflows is we introduced Java that managed the memory for people, right? So making these things super easy is actually the way to secure it. If you could leave the development community with one tip on end-to-end encryption, one thing that they should do, and it's not use Ockam, though hopefully they all do, but what is the one thing that they should be considering to help secure the communication of their applications?
Think about the risk to the communication of your data. So in the last few years, there's been a lot of conversation about risk that comes from dependencies, right? And I think that's been a fantastic direction because we're talking about, hey, if there's a new piece of code inserted into my code as a dependency, then that means that 5, 10, 15 developers over there of that thing could do something maliciously, either intentionally or if they're compromised, that could affect my risk posture, right? So we've been thinking about this. But the thing that we think less about, or there's less conversation about, is if I make a third-party API call, risk is really just a proxy for how many people are involved, right? So how many people are behind that API call that could potentially be attacked, be vulnerable in some way, or be compromised in some way? And if my data is being exposed over there, then what are the odds of that data being compromised, given that's a 10,000 person company with 500 of them having direct or indirect access to that piece of information? So thinking about risk and dependencies in this way is incredibly insightful. And oftentimes I used to do a presentation where I'd be like, if you draw this in, if you take people as a proxy for risk, the number of people in your dependency chain at build time is an order of magnitude, if not two, lower than the number of people in your dependency chain at runtime. And so think about the risk at runtime to the flow of the data, and then think about removing that risk in various ways. Ockam is one way to do it, but there are other ways. Encrypt your data when you're storing it, et cetera, et cetera. There's all sorts of ways to approach it. Don't send your data to certain destinations. That's also a way to remove that risk, right? But I guess my tip here is think about the risk at runtime to data flows.
And I like the implicit recommendation in that, which is to do threat modeling. Think of it outside of just the technology itself, which is really do a threat model of the risk that is faced by the application. Well, that's fantastic. Thank you for joining us today, Mrinal. That was awesome. I love to geek out on these networking technology things. I'm never sure if developers, the broader development community is interested in networking, but I have been and always will be, simply because I think most security issues at the end of the day do come down to networking and networking security and performance. So Thank you for joining us today on The Secure Developer, and we'll catch you next time.
Thank you. Thanks a lot, Danny.
Thanks for tuning in to The Secure Developer, brought to you by Snyk. We hope this episode gave you new insights and strategies to help you champion security in your organization. If you like these conversations, please leave us a review on iTunes, Spotify, or wherever you get your podcasts, and share the episode with fellow security leaders who might benefit from our discussions. We'd love to hear your recommendations for future guests, topics, or any feedback you might have to help us get better. Please contact us by connecting with us on LinkedIn under our Snyk account, or by emailing us at thesecuredev@snyk.io. That's it for now. I hope you join us for the next one.